Thank you very much, John, and thanks to the organizers for the nice invitation. It's a real pleasure to be here. Unfortunately, I'm going to be here only today, but it was not planned, and I'm really sad about that. All right, so I'm going to talk about the Milnor conjecture for the Rham-Witt complex, and let me start with the Milnor conjecture. There you go. So the Milnor conjecture is a relationship between Milnor K-theory and the Witt group. And there is something you can do also for the Rham complex, and there is a similar isomorphism like that. So the plan for the talk is roughly the first half. I'm going to be explaining these two statements, and then I'm going to try to relate them a bit more than just visually, like I did there. And then I'm going to try to extend these two results to some other functors and see what comes out. So that's the plan. So let me spend some time in talking about this, this board up here. So first, let's talk about Milnor K-theory. And Milnor's conjecture. Okay, we start with a field. And so far, it can be of any characteristic. Eventually, I'm going to take it to be of characteristic 2. But the Milnor conjecture makes sense for every characteristic, and in fact, it's probably even more interesting for odd characteristic. And you know, and let K star be the algebraic K group. Okay, and let's start computing them. We can take K naught. You know, these are just finite dimensional vector spaces, modular isomorphism and group completed, and these are characterized by the dimension. As just said, and then you can take the first K group. You know, and this is defined as a quotient of the general linear group, and we can take the determinant and look into the units of our field, and this is also an isomorphism. And then we can also look at K2. It is a bit more complicated, but it's still describable, and it's a quotient of the tensor product of two copies of the units, modular relation that identifies a tensor or kills this quantity for a greater than 0, 1. It is a theorem of Matsumoto. And then, I mean, there's a bit more we can say for maybe K3, but otherwise, that's it. And so, what did Milnor do? He says, well, let's be very optimistic and define something that, you know, is those three things in low degrees, and then is the freest possible thing that algebraic K-theory could be. So he defines Milnor K-theory to be, you know, if you look at the first three groups, it's basically the tensor algebra of K modular relation in degree 2. So take tensor algebra of, sorry, not of K, of the units of K, and we mod out by the relation that here we are looking at the units as an abelian group under multiplication. As an abelian group, you can take the tensor algebra over Z and mod out by this relation in degree 2. This is a graded ring. And I mean, by construction, there is a map of graded rings from this thing in algebraic groups. And this is not an isomorphism in general. Questions so far? All right. Then what does Milnor's conjecture say? Well, he describes this thing modulo 2 in terms of symmetric forms over K. So it relates this K theory to symmetric forms. So here we go. Let me remind you. So now we define the left thing on the top isomorphism. Let me move on to the right one. Let me remind you the definition of a form from linear algebra. So non-degenerate symmetric form over K consists of a pair of a finite dimensional vector space V and a form, what's the form of V? And it's an isomorphism V from V to V dual. So let's see, this is a form, it's non-degenerate because it's an isomorphism, and I'm missing symmetric. And symmetric means that this isomorphism is self-dual in the sense that you can do this, but you can also identify canonically V with its double dual. And phi defines also a map from here to here, which is phi dual. And I mean, in other words, if you want to think of this map as being a pairing on V instead, this is equivalent to saying that the adjoint, which is a map from V tensor V to K, satisfies that. These conditions. Okay, so that's a form. And I'm building towards defining I, which is the kernel of something, and the domain of that kernel is this Witt group. So to get to the Witt group, I need to say what a Lagrangian is. Well, Lagrangian of a form consists of a vector subspace of V, such that two things happen. First is that if I take my form and I restrict it to this subspace, I get 0. And the second one is a non-degeneracy condition that if you take the inclusion and project to the dual of this Lagrangian, you get an exact sequence. It's exact. Where, let's see, what is this map? This map is you apply your phi to the dual, and then you take the dual of the inclusion. Call this map I. Okay. So this is the definition of a Lagrangian on a form. And now we can define the Witt group. Okay, is so we take the set of non-degenerate symmetric forms on V, and to really make it a set, we take isomorphism classes. And then you can take direct sums of forms. So this gives you a monoid. And it looks a bit like if you did algebraic K-theory. So if you were doing algebraic K-theory, you would take the group completion of this monoid. But we're not going to do that. Instead, we're going to take this monoid and quotient it by the Lagrangian relation. So we quotient by the forms, subgroup, submonoid generated by those forms, which admit a Lagrangian. So definition of the Witt group. So it's a monoid by definition, but it turns out to be a group. And it's not hard to see that if you take the class of a form and you wonder what its inverse is, that's just given by the same vector space but with the form with the sign inversion. And the reason is that if you add up the one on the left and the one on the right, you can look at the diagonal inside, and that's a Lagrangian. So we have constructed a group, and now I guess we're almost there into defining this side. Isomorphism. Is in fact a group by the, so that's a property, but also a ring under the tensor product. And then we can define I to be the kernel of this multiplication map, which is a ring homomorphism. Sorry, this computation. And so what does this do? It sends the class of a form to its rank. Let's say the dimension of V. There's nothing to do with the form. And the fact that it's well-defined modulo 2 is that, well, if you think of our Lagrangian thing, because that's exact, these are vector spaces, so it says that V is non-canonically the sum of L and L dual, and so L and L dual have the same dimension, so the dimension is to be even. So if you have a Lagrangian, you better go to, you are 0 here, so you better go to 0 there, that's what it was. Okay, and then this conjecture of Milnor is that in about 1970 is that if you take this Milnor K theory mod 2 and you map it to the gradient associated to the power filtration of this ideal, and let's define the map. So I mean, this is sort of generated by something in degree 1. It's a tensor algebra, or the quotient of a tensor algebra. So, and in degree 1 we have the units of k. So I need to take a unit and send it somewhere. And I'm going to send it to an element in the ideal, which is given by 1 minus the one-dimensional vector space together with the form which is given by the matrix, which is multiplication by this unit. Since this pair is a one-dimensional vector space with a form given by the matrix A, and 1 minus that is going to be, because K is of dimension 1, 1 minus that is going to be in the kernel of the multiplication. And the map, and there is a and right, maybe just a few words about the proof. So this makes sense for every field, and it was conjectured in the 70s. It was proved in 82 in characteristic 2, and the proof is relatively elementary. I mean, it's not as simple, but it's somewhat elementary. And then for odd characteristic, this was proved in 2007. So there's a big gap in between, and it uses Warwick's motivic homotopy. So there's a comparison between these two and entitled homology, and that's how. So it's much more involved in odd characteristic. And for the purpose of this talk, actually I'm going to be focusing on this case, characteristic 2. Okay. So are there questions so far about the statement of this? All right. Yeah.
Why do you use the tensor algebra? Everything else looks commutative to me. Why don't you use the symmetric algebra?
I don't know. Because otherwise it's not true anymore. Isn't it? I mean,
it becomes symmetric.
sorry?
It becomes symmetric.
Becomes symmetric. Oh, by that relation?
Yeah.
Ah, there you go. Thank you, John. Okay. Right, so but we're going to see in a second, I'm going to try to talk about this statement here, but the general question is what happens if you do try to do this type of statements for something different than algebraic K-theory? What about something else? Okay, and I mean, of course, what else would you do if you want to change your mind? You know, if you want to do something else than K-theory, you try to do topological Gaussian homology. So this is section 2. Is topological Gaussian homology. So, and I'm going to try to explain that if you try to run the same type of construction for THH, you're going to end up with the second statement over there. And the proof is going to be way simpler. So I'm going to stick with my field K, and then, I mean, Beckstedt defined he defines topological Gaussian homology of K, and I mean, for now I can just define it as the tensor product of two copies of K over the enveloping algebra of K. But I'm going to look at them, you know, I'm going to take Eilenberg-McLean spectra everywhere, and this tensor product here is over the sphere spectrum. Smash them in the category of spectra, and at least for now, this is infinity ring spectrum. And you can start calculating. So what happens if you do the same as we did for K theory. Yeah? So I0, that's just K. That's fairly clear. I mean, it's just the same thing if you did it in algebra, and then if you do strict tensor products, you get K. Something a bit more fun is pi 1. If you do this in degree 1, you find Taylor differentials over K, of K. And then maybe you can do a couple more degrees. But this already kind of tells us, you know, what this, or at least, I don't know if it tells us, but it gives an indication of how we could construct something free out of this. We can just take the Rham complex. So, we can define Rham complex K. This is just the exterior algebra on omega 1. And I mean, what's the relationship between this thing and the Rham and Milnor K theory? Well, there is a diagram. So we had, before we had Milnor K theory of K, this was mapping to the algebraic K groups. And you know, there is this famous trace map to the homotopy groups of THH. But this has an analog over here. You put the Rham complex. Maybe I should have said something. So, I mean, this is the free CDGA on K with maybe, I mean, we need to watch out a bit in characteristic 2, at least on how we define the exterior algebra, but this has this relation in. And now, these homotopy groups also have a differential that comes from the circle action, and because that's free, and you get K in degree 0, you get a map here, kind of like this map here. It was also a free thing, so you get a map. And you can fill out this square with the map here that sends, so again, this is generated in degree 1. You can send a unit to this differential divided by A. So this is a nice picture that relates these 4 things. I mean, I'm just using this as a justification that somehow the Rham complex has the role of Milnor K theory for THH. Sorry, sorry. Okay, so we define. So we define this thing, and then okay, what about this? Well, it's almost all there. So now let me take really K to have characteristic 2. And then I can look at the squares inside of K. And because the characteristic is 2, this is an additive subgroup, so that's a subfield. And I guess I can define now J to be my ideal, which is the kernel of the multiplication map from, it's a subfield, so I can regard K as a vector space over this field and tensor them together. This. And then there's a proposition, it's not even theorem, that the Rham complex of K is isomorphic to the gradient associated to this power filtration from this idea. Okay, and now, I mean, I stated here with a mod 2. Now, if K is of characteristic 2, I don't need to mod out 2. 2 is 0 in here. I can mod it out if I want to. But the point is that if you could do the same construction in not characteristic, but as soon as 2 is invertible, well, of course you keep 2 here, so you get 0. But this ideal is also 0 because this map is an isomorphism, it turns out. characteristic is not 2. So this is really interesting only characteristic 2. And I mean, the proof is fairly simple. So here it's classical. So Kata, in fact, uses this statement in his proof of Milnor's conjecture in characteristic 2 with no comment whatsoever. He just says that it's clear. And then there is a note online in the 2000s of on Anderson's website where he says, well, he couldn't find the proof anywhere, so he proved it. And it's not too bad. I mean, you just pick a 2 basis for K, and then you basically, it's a linear algebra argument. All right. And I mean, I guess the point I'm trying to make is that these are strikingly similar, these 2 statements, and it's suspicious that there is this square relating them. So what is going on? Okay, so let me try to relate them in a way which is slightly more precise than just a aesthetic thing. So let's try to relate these 2. So let me try to give, and this is the only bit of the talk where there's some equivariant homotopy theory. And it comes in, it's just a motivation for comparing these 2 things. It doesn't come in a very relevant way. On the other hand, well, you're going to see later, this is actually important. So let's look at the Milnor conjecture side first. So we start with K theory. And there is a preferred, and I wish I had something more specific to say here, refinement of algebraic K theory to a Zemo 2 equivariant spectrum with the property that those bit groups that come up in Milnor's conjecture is in fact pi 0 of the geometric fixed points of this refinement. Okay, a bit more than that. So I want to argue that this, this side here has to do with the equivariant homotopy theory. Let's try to. What about the map? Well, so we have this dimension map to Zemo 2, but here we have a restriction map on this side. Although I need to watch out a little bit. So if I took genuine fixed points, this would go to the underlying spectrum. But because I'm taking geometric fixed points, I'm landing into the Tate construction, and so pi 0 is going to be phi naught mod 2. But I mean, phi naught of K here is Z, so Z is a canonically, and these maps match. So in other words, one could say one shouldn't, but one could say that Milnor K theory mod 2 is isomorphic. I'm going to write the same thing as before, but now I'm going to change my ideal. I'm going to say it's the kernel of this restriction map. So what are we doing? We are studying with K theory. We are building something freely, roughly, out of the lower groups and get something. And then we are also refining it to something equivariant, and we get this isomorphism. But this is the equivariant bit, and this is the free bit. So now I can do the same with THH. There is a preferred. Maybe I should say some names. This is, I guess, this is due to Hasselt and Madsen. And I guess, I mean, then when this is a bit of a long story, but I guess probably pi naught was already known. Let's leave it at that. And sort of in the same way, one can construct this refinement. You can do the same on THH. So there is a preferred refinement of THH. Okay. So as a MO2 spectrum. And I mean, this is again due to Hassel-Madsen. And the property that, so let's see what happens here. If you take pi 0 of the geometric fixed points, or this thing, this is indeed 2 copies of k times over the squares. And moreover, you can do the same trick. You look at the restriction map. This lands into pi naught of THH of k mod 2. But I mean, if k is of characteristic 2, then just mod 2 doesn't do anything. And this corresponds to the multiplication map of, I guess I should say, pi naught of THH. And this is isomorphism. So the same kind of thing is happening here. So then what we get is that take the Rham complex of k, that's the same as the graded, where J is the kernel of this restriction. So this gives a bit of a more precise link between these two statements. Yeah.
Talk about the CMOT2 spectrum structure. Are you secretly giving k an involution, or is it coming from elsewhere?
Yeah, that k is the trivial involution in this case. It's commutative, so that's fine. Yeah. Yeah, I don't know exactly what happens when k is not trivial involution. Nor what happens, I mean, also if k is not a ring, that is not a field, then it's a bit weird. I mean, the Rham thing works a bit better. I mean, I1, for example, is always omega 1 for every commutative ring. But, yeah. Yeah. Other questions? So, but let me say that so far, you know, nothing has happened. I mean, nothing new. It's just a reinterpretation of the theorem by pushing in some geometric fixed point somewhere. But now, maybe, now that we found a pattern, maybe we can try another functor where we do get something new. So, what's the next thing to do? If you've done THH and K theory, then the next thing to do is to do TR. So, Rham-Witt complex. And Milnor conjecture. So, it is Brooksted, Chang, and Madsen. What they do is that they look at THH and they refine this further to a spectrum with direction of a finite group, for a finite cyclic group. So it's refined to a CN spectrum. this is the cyclic group of order n, and you can do this compatibly for every n. And no.
C no.
What is C naught? Isn't that still a trivial group? Okay, so, and then one can define TR star of k, and I mean, we pick a prime too, which eventually is going to be the prime 2, and we can define this to be pi 0 of, so like this, TR, TR n, right? So we take the genuine fixed point of THH by the cyclic group of order p to the n, for all n greater or equal than 0. You know this, right? And take some of the groups. And then we start computing in low degrees again. So here 0. This turns out to be the ring of bit vectors. Okay, truncated at the truncation set p to the n. So this is called the n plus 1 truncated p typical bit vectors. So not to be confused with the bit group we had before, it's something else. And what's the standard example is that if you apply this construction to fp, you get z mod p to the n plus 1. Okay. That's a funny thing. And this is not easy. It's a proper theorem. That's from Madsen. And then, well, that was very hard. And then if you do TR1 and plus 1, you get almost Kähler differentials on this, but not quite. So you get a quotient of that. Complicated quotient. And then, I'm not sure if we know what's going on with degree 2. But maybe it doesn't really matter. We can try to define something free out of these two groups. But free as a what? That's a bit tricky. So we need to look at what kind of structure we have on these homotopy groups. For THH, we had a differential coming from the circle action. But here the structure is much more rich. And it has to do with, with the groups that can also vary. So, there are operators on these groups. So we have, if we take this coordinate prime. So if we take this group, and this one, there are maps, let's see, there is one here called B, and two there called F and R. And a differential that comes from the circle action, and they satisfy some axioms. And such a thing is called a big complex. So that's called a bit complex, and the definition is, again, using myself, Madsen, I mean, in these terms, but it really goes back to, I guess, Bloch, Lean, utility, and is that while one can define this Rham-Witt complex, there's two things. Because it's a pro-differential graded object and is the initial object in the category of things with that structure. So in the category of, let's see, of objects with the structure of this TR. I mean, none of this is obvious. I mean, it's not even clear that there is an initial object in this category. And so that's their definition. But then there was a previous definition in terms of generators and relation that was very complicated. Do I think Bloch in low degrees, and then Deline and Lucy generalize it to higher degrees. And I mean, they also give a comparison between this new definition and theirs. And I mean, it's just hard. I mean, it's hard to describe what this is explicitly. It's not so easy. Okay, so this is going to be, you know, our left-hand side version of this isomorphism that we sort of built out of TR by looking at these low degrees and building something free out of it. And then let's do the equivariant homotopy theory bit on the other side. So similarly, there is also refinement refinement of TR of K times P to as a multispectrum. Let's see. I think Wittgenstein was the first one writing it down, and now, well, we can try to do the same thing. So we can say that J be the kernel of this restriction map on geometric fixed points from pi 0 of TR of K. And now let me take the prime 2. So I can do this and take the restriction map to pi 0 of TR, K at the prime 2, module 2, which, you know, the underlying thing is the thing we know, it is the bit vectors. So that's the two typical bit vectors of K. and assume that the characteristic of K is 2. Oh, well, I guess we don't really need to. Oh. And now the same thing is going to hold. Sorry?
You want to write gauge vectors mode 2?
Oh, yes, thank you. Yeah. Thanks. So theorem is that if you take the Rham-Witt complex, okay, and 1 of 2, this is isomorphic to the graded associated to this relation, the powers of this idea. And so first one needs to build a map, and this is the initial object is in a certain category. So the way it goes is that we need to produce the same structure over here. And that's already not obvious. And the operators on this side come from equivariant homotopy theory. But the proof has nothing to do with homotopy theory. So with equivariant homotopy theory, it's purely algebraic. So let me maybe write a couple of remarks. So if the characteristic of K is equal to 2, sorry, it's different than 2, then, well, if 2 is invertible in K, then it's still invertible in the Rham-Witt complex, so the left-hand side is 0. But similarly, also the geometric fixed points of these are also 0 as a spectrum even. So this theorem doesn't tell you anything. It has content really only when K is of characteristic 2. Then so as I was saying before, equivariant homotopy theory only helps us trying to figure out what the statement could be, but the proof is completely algebraic. So the proof goes like this. First, you compute the homotopy groups of these geometric fixed points of TR explicitly, and in particular the ideal. So you give generators and relations for this ideal, and then you prove algebraically that those two are isomorphic. It's not going to be by definition the same. I mean, you do need to work also for the algebraic proof, but it is algebraic. So it is computational in a sense. And it implies. This is a Rham-Witt complex, mod 2 algebraic. So it would be really, really nice to have a proof of this that doesn't compute J, but that uses somehow homotopy theory. But I don't know what that would look like. And then maybe just to finish, so we've done K theory, THH, and TR. There's one more thing to do, which is TC. So there is also a version for TC. And I tried for a while to just get a proof that is completely algebraic, like I did there, but I couldn't. But you can basically input the Milnor conjecture twice and get the statement, get a proof for that. So But the proof, well, it is basically equivalent to the Milnor conjecture. But I mean, but you need to invest some work, so it's a bit complicated to see how all these results fit together. But I wish I had an independent proof of that is purely algebraic, but I don't. Okay, I think my time is up.
Questions? Oscar. So the geometric fixed points of K theory is like L theory, I guess symmetric L theory in this case. And like for TC it's supposed to be normal L theory.
Yeah.
What about TR and various intermediate things? Do they have some L theory?
Not that I know. Not that I know. But I mean, in the case of fields, you can give a completely. The thing is, none of this has to do with L theory. So even Milnor conjecture, the way it's proved, you just write down the bit group, you write down an algebraic presentation, and then you prove it with that. And here it's similar. You have TR, you can just describe it as a spectrum, the whole geometric fixed point spectrum, completely for fields. You can work with that. But I mean, to answer your question, I don't know.
Anne-Marie?
Does your algebraic proof of this result, can you see from the description of J that J star over J star plus 1 is initial?
Does it give me what, sorry?
Can you see the initialness?
No. So the proof is by induction. So the initialness gives you a map.
Yeah.
Yeah. And then there are some nice exact sequences relating the various degrees of this with the R map, and you do induction on those. No, yeah, it would be cool to see. But there isn't, yeah, it does give you some sort of formula for, at least you have a formula for pi 0 of the geometric fixed points of TR explicitly, and you have generators for J as an idea in there. And so that's as close as about, and then you need to do this, and that's hard, but that's the best description you can get of that thing.
On the left-hand side here, there's the presentation of the bit non-bit complex across this foreseeable values and R operators and this very so are they corresponding? So when you basically make a calculation of J dot, in what terms does that make? If you have
Yeah.
ways
So
of producing elements there.
yeah. So pi 0 of TR with the geometric fixed points. That's a well, actually, even without pi 0, this is a pullback. It's a long iterated pullback with, I think, roughly 2 n terms of things of the form k tensor over S with k. Let's stick to pi 0, to be sure. I mean, you can, all of the homotopy groups have a description in those terms, but let's say like that. It's a long pullback of those, and then the restriction map is going to be yeah, it's complicated. It's defined in terms of norms and restrictions, and you can give some elements here that generate the ideal. It's a little bit like when you say, A tensor B plus B tensor A generates omega 1. It's going to be a little bit like that. But now this is going to be one of these copies, and then you're going to have 2 to the n. And I can tell you more later. But it's not it's explicit, but not super easy. And the fun thing is that now this V, F, and R over here, you can also describe it on generators, but they do come from the operators. You have this Imo2 action is from some dihedral structure, so you have the V, R, and F are dihedral equivariant maps. So you can take cyclic fixed points first, and then Imo2 fixed points later. So all of those do come from the usual topological R and F and B. The funny thing is the differential that comes from the identity plus the Weil action of well, let's read for the low secret groups. Zermo 2 sits inside the dihedral group of order 2, and the Weil group is C2. And that C2 here gives you, so that Weil action gives you some residual involution on the geometric fixed points, and that gives you the differential.
So I had a question. Are these CMOD 2 refinements, are they something to do with THR? Or
Yeah.
you,
Yes.
You got to tell us anything about that?
Yeah, that's what it is. I mean, you know what? Yes. So the Zermo 2 equivariant spectrum is called THR. Okay.
In what sense are those refinements preferred?
Right. I mean, if you want the same pattern to reproduce in all the examples, you need to talk about Poincaré categories, and then there is a canonical Poincaré structure. Canonical is not. There's a preferred Poincaré structure on the category of modules over any discrete ring, and that preferred one is going to give you this equivariant refinement. But I mean, there are many, and yeah.
You haven't answered the question.
Sorry, this is THR of K. It is what the Zermo 2 spectrum is. What was your question?
Why are they preferred?
I don't know. I don't know. I mean, so if you take, if you think in point-set models and you take a commutative ring and you want to make it equivariant, that's how you do it, and that's what comes out. But there are other ways of doing it, and that turns out to be the one. I don't know why.
There's the geometric. You can turn ahiscobordisms upside down, so there's an evolution on this ahiscobordism space, which gives you an evolution on algebraic K theory, and this is the one that it's that's it.
Well, but it's not. I mean, that's how you do the THH bit. But you input something equivariant, right? And it's not clear why. And there are, if you start with a commutative ring, there are many ways of making the input equivariant. You can do the sort of, you need to declare the fixed points. You can do that to take the fixed points, but you could also take orbits, for example. That's what gives you symmetric or quadratic L theory, for example. And it's not completely clear to me why that's the symmetric one that comes out. That's what I want to say.
Are there more questions? If not, we should thank Emanuele again.